Hello there, and in this video we're going to work through another example of integration by trigonometric substitution. So let's look at what we talked about last time. So last time we looked at how we can solve the integral 3x times the square root of x squared plus 5 using trig substitution, namely x is equal to the square root of 5 times the tangent of theta. Now we were able to use just normal substitution to sort of check our answer, but what if we actually don't have an option? So let us look at this example, namely the integral of dx divided by the square root of x squared minus 6x plus 13. Alright, so the first thing I'm going to do is try and work it into, let's see, since the leading coefficient of x squared is positive, I'm going to try and form this in the form 1 plus u squared. Because if that is the case, then I can just let u be equal to the tangent of theta, and then when I square that, it's going to give me 1 plus tangent squared, and then this, which is secant squared. The secant squared and the square root are going to cancel, just leaving me with secant, and then I can go from there. So how can I get it in this form? So one thing I can do is complete the square for that quadratic. So I can rewrite this as the integral of dx divided by the square root of x squared minus 6x. So I'm going to focus on the minus 6, so take that divided by 2, that gives us negative 3, and square it. So I'm going to add 9, subtract 9, and then we still have that 13 left over. So if that's the case, then I'm going to factor those first three terms. So that's going to give me the integral of dx divided by the square root. So x minus 3 times x minus 3. So x minus 3 is a quantity squared. And then 13 minus 9 is going to be positive 4. So from here I'm going to factor out a 4 out of this bottom. So once I do that, that's going to give me the integral of dx over the square root of, so I'm going to pull out a 4. And that's going to give me x minus 3 squared divided by 4 plus 1. And then I can take the square root of 4, that's going to give me 2 on the outside of the integral. It's a constant. So we have 1/2 times the integral of dx all divided by the square root of 1 plus x minus 3 divided by 2, the quantity squared, because 2 squared gives us 4. From here, I'm going to let u be equal to x minus 3 divided by 2. So du is going to be equal to 1/2 of x dx. So that means dx is going to be equal to 2du all over, wait a minute, no, just 1/2, because that's a linear function, so 1/2 dx. So dx is going to be equal to 2 du. Yeah, if that other thing was the case, then we would have a little bit more of an issue. So this is going to be equal to 1/2 times the integral, so dx is going to be equal to 2 du all over the square root of 1 plus u squared. And we see that the 1/2 and the 2 will cancel, which is nice. So then we have the integral of du all over the square root of 1 plus u squared. So now we've set up our integral ready for trigonometric substitution. So now we're going to let u be equal to tangent of theta. So if that's the case, then that means u squared is going to be equal to tangent squared theta. We can add 1 to both of these sides, and that's going to give us secant squared theta. So that means if we take the square root, that's just going to be equal to secant theta. So the square root of 1 plus u squared is just secant theta. So you have this equal to the integral of du all over secant theta. And the reciprocal of secant is going to be cosine, so this is just going to be equal to the integral of cosine theta d. Wait a minute. That's going to be du. But what's du? So du is going to be equal to secant squared of theta, d theta. So let's replace that du here. So du is going to be equal to secant squared theta d theta. Let's rewrite that back in terms of secant. So one of these secants will cancel, so that's just going to be equal to the integral of secant of theta d theta. Now this integral is actually in a workable position, so how can we find the integral of secant theta? So one way we can do this is we can multiply top and bottom of this fraction by secant theta. That's going to give us secant squared theta divided by secant theta d theta. And let's see, how do I want to do this? Actually, no, I don't want to do that. I like working with cosine more. So that's going to be equal to secant theta d theta, which is the same as 1 divided by cosine theta d theta. Most people will be more comfortable working with cosine rather than secant. So now I'm going to multiply top and bottom by cosine. So that's going to be cosine of theta divided by cosine squared of theta d theta. And then I can rewrite cosine squared as 1 minus sine squared. So we have cosine of theta divided by 1 minus sine squared theta d theta. And from here I can use a u substitution. I'm going to let w be equal to sine of theta. So I'm focusing on this sine here because his derivative is located up top, so I should be able to cancel that. So dw is equal to cosine of theta d theta. So d theta is going to be equal to dw divided by cosine theta. So that's going to be equal to cosine of theta divided by sine of theta is w, so this is going to be 1 minus w squared times d theta is going to be dw divided by cosine of theta. So our cosines cancel as desired, so this is just going to be equal to the integral of dw divided by 1 minus w squared. And this is an inverse hyperbolic function, so it's going to be equal to inverse, so arc, and which one was it? So if it's 1 plus w squared, that would be arc tangent. So if it's 1 minus w squared, that's going to be arc hyperbolic tangent. So arc hyperbolic tangent of w plus c. Alright, now that we have evaluated our integral without working backwards through our substitutions, all we need to do is just work back through our substitutions and we should be able to get our final answer in terms of x. Alright, so let us first recall what w was. So w was equal to sine of theta. So let's replace that first. So we have that this is arc hyperbolic tangent of sine of theta plus c. And also recall that theta is equal to arc tangent of, let's see, what was theta? Let's go back here. So if u is equal to tangent theta, so if u is equal to tangent of theta, then theta is going to be arc tangent of u. Okay, so that's going to give us the sine of an arc tangent of something, right? So let's bring out a triangle to sort of see that out. So we're in the process of evaluating the sine of the arc tangent of u. So let's see if we can figure out another way of writing this. Alright, so let's work a right triangle here. Let that be theta, let that be a right angle. So the tangent of theta is equal to u. And we can rewrite u as u divided by 1. So remember, tangent is equal to opposite over adjacent. So we can let the opposite of theta be equal to u, and the adjacent of theta to be equal to 1. If that is the case, if I call that r squared is going to be u squared plus 1 squared. So that means r is going to be equal to the square root of u squared plus 1. So this is going to be the square root of u squared plus 1. So now, therefore, I want to find the sine of theta. So remember, sine of theta is going to be opposite over hypotenuse. So that means the sine of theta must be equal to the opposite, u, divided by the hypotenuse, the square root of u squared plus 1. Alright, so let's go back to our problem. So our integral of interest was equal to, where did we stop? Arc hyperbolic tangent of sine of theta plus c. So now we have sine of theta, so this is going to be equal to the arc hyperbolic tangent of sine of theta, which we found to be u divided by the square root of u squared plus 1 plus c. And now we go back to the original u. So let's see if we can find what u is equal to. So let's scroll back up. Where's our u? U is equal to tangent theta. U is equal to tangent theta. So if u is equal to tangent theta, what can we do with that? Actually, wait, no, that's not the u that we want to go with. I should have named them different variables. I should have let that be like v squared instead of u squared to sort of avoid the confusion. So we don't want that u in terms of theta, we want the u in terms of x. So u is equal to x minus 3 over 2. So u is equal to x minus 3 over 2. Yeah, we're trying to go back to x, so we should jump there. So this is going to be equal to the arc hyperbolic tangent of u, so 1/2 x minus 3, all over the square root of, what is that, x minus 3, the quantity squared, divided by 2 squared, which is 4, and then plus 1, and then plus c. And then we can, let's see here, what can we do? So we can multiply top and bottom of this by 4, right? So this is going to be equal to the arc hyperbolic tangent of 1/2 x minus 3 divided by, and then we have the square root of x minus 3 squared plus 4 all over 4. So we have 1 divided by 1, but the square root of 4 is going to factor out and gives us a 2 there. And that 1/2 and that 1/2 is going to cancel out with each other. So this is going to be equal to the arc hyperbolic tangent of x minus 3 all over the square root of x minus 3 squared plus 4 plus c. And we can probably stop there if we want. So therefore, what do we have? So we have that the integral of dx divided by the square root of x squared minus 6x plus 13 is equal to the arc hyperbolic tangent of x minus 3 divided by the square root of that term, x squared minus 6x plus 13, because that's what that, completed the squared into. So definitely a lot of different tools and techniques that went in here. A couple substitutions. Definitely don't try and avoid confusion which direction of u you're going to. We also used a little right triangle to figure out the sine of arctangent of something, and we also used some trig substitution to sort of, that's the goal of this video, is how to use trig substitution. The 1 plus tangent squared trick is the most common one, but using sine squared plus cosine squared identity is also commonly used. So keep all these things in the back of your mind when you have a square root of a function, because they're usually the ones that you want to go to.